Welcome to this week's topic, which is the refraction of light and the index of refraction and total internal reflection. So the last couple of weeks we've been dealing with plane mirrors or curved mirrors, and we've been dealing in reflection. That's when things reflect off of the surface of something. Now we're going to go, well, what happens to light when it goes in through something? And that's refraction. So first we're going to learn what refraction is, what causes it. We're going to calculate the index of refraction, and we're going to use the index of refraction to determine whether the light is going to bend toward or away from the normal in a medium. We're then going to learn about total internal reflection and when it happens, and then how that internal reflection is seen in the world around us. So refraction is basically the bending or the change in direction of light when it travels from one medium to another. If you've ever put a straw or an oar or anything from air into water, it almost looks like it bends at the surface of the water. We know it didn't bend, it's a straight straw, but when we put it in, it bends. Here we have a glass with water in it or wine, and as the light is passing through the glass, through the wine, through the other side of the glass, it totally distorts the image that we see. So what causes it? A good way to describe this is thinking of a car going from pavement. It's going very fast, but as soon as it hits that sand, it slows down. That's if it's going straight. If it's going on an angle when it's in the pavement, when it hits the sand, it starts turning inward as it hits the sand. That's what's happening to the light. When the light is coming straight in, it's going at a certain speed, and then when it hits the new medium, it slows down and keeps going straight. But if it's traveling at an angle when it's coming into the medium, it starts bending, and it will either bend toward the normal or away from the normal. And this is what we call refraction. The spitfish here, to capture his prey, will spit up at the bug, and then the bug falls in the water and eats it. So the bug is actually here. But what happens is in the water, as this guy is looking at it, the light ray is leaving his eye, it bends away from the normal, and it looks like the bug is here. So if he spits here, he's going to be spitting onto a branch that doesn't actually have the bug. If you put a pencil into water, it almost looks like it blew up, it got wider. If you move it a little to the left in the water, it almost looks like it has a bend in it, or it's in two pieces. And the more you bend it, the more exaggerated. So the more you put it on an angle, the more exaggerated that bend becomes. Oops, I forgot to play the video.
Light rays travel through space in a straight line at approximately 300,000 kilometers per second. As light passes through a transparent medium such as water or glass, its speed is decreased. For glass, it's reduced to 200,000 kilometers per second, and for water, the speed is 225,000 kilometers per second. If the light enters into a medium perpendicular to the surface, it passes straight through, but at a slower speed. However, if the light beam arrives at the medium surface at an angle, not only will its speed be reduced, but it will bend due to a process called refraction. To better visualize this phenomenon, let's look at this diagram. As a beam of light reaches the surface of a medium, the lower portion enters first and is slowed down. However, the upper portion is still traveling at the speed of light until it arrives at the surface and enters. This speed difference at the top and bottom aspects of the light path causes it to pivot, bending toward what is referred to as the normal. This is an imaginary line drawn perpendicularly to the surface of the material. Transparent materials have what is called a refractive index. This is the speed at which light travels in a medium compared to light traveling in a vacuum. For example, typical glass has a refractive index of 1.33. This is calculated by dividing the speed of light in a vacuum, 300,000 kilometers per second, by the speed of light in glass, 225,000 kilometers per second. The refractive index of air is 1.0003. Anytime a light beam travels from a medium with a low index of refraction, like air, to a medium with a higher index of refraction, like glass, the beam of light will bend toward the normal. Likewise, when the beam of light exits a highly refractive medium into a medium with a low index of refraction, the process is reversed. The bottom portion of the beam of light exits first and resumes at the speed of light, with the top portion still at the speed determined by the medium. This causes the beam to pivot away from the normal line.
Sorry. Okay, so what causes refraction? It's the speed. So the light is traveling at a certain speed, and then when it hits a media or a medium, it slows down or changes speed, and then that determines whether it bends inward or outward. The more the light slows down, the more the light is refracted, and when the light from the spoon passes from water into the air, the light rays are bent. And this makes it difficult to judge the actual location of an item. So here we have a treasure chest, and the light is traveling up from the treasure chest, but when it hits the air, it speeds up so it bends away from the normal. But our little human eyes only see that light travels in a straight line. So we extend that refracted ray straight out into the water, and we think the chest is floating in the middle somewhere here. We think that's where the chest is. The bent spoon. Light from the spoon travels from water to the air. It'll bend away from the normal. So as it's coming out from water into the air, it bends away from the normal. Our brain assumes that, again, that light travels straight. So when we look at that refracted ray, we go straight backwards, and that's where we predict the image to be. Therefore, the spoon appears to be displaced. So here we have this straw going in, and it looks like there's actually two pieces of straw. It's not even together. Here again, the spoon is here, and then there's a little break, and the top of the spoon is over here. So the speed of light in a vacuum of space is 300 million meters per second, or 3.0 times 10 to the 8 meters per second. The particles in medium slow down the passage of the light waves, which results in light traveling more slowly through a block of glass, for example, than it travels through the vacuum. Now, the idea is that as light is coming in from the air into a medium, it will refract once as it goes into the medium. And once it's in the medium, it travels at a constant speed all the way through to the end of the medium, where it then refracts again. So the speed of light in a vacuum, as we said, is 3.0 times 10 to the 8 meters per second. And that's not for all things though. So we use the symbol V for speed of light in a medium. In a vacuum, there's nothing in the way, nothing to slow it down. So it's 3.0 times 10 to the 8. Whereas in water, it's 2.26 times 10 to the 8 meters per second. And in acrylic, it's 1.76 times 10 to the 8 meters per second. So there's basically three rules. The first is that all of the rays, the incident ray, normal, and refracted ray, are all in the same plane. It's kind of like a Cartesian coordinate system. It's like an XY axis, and all of them are lying on that plane. So there's no 3D here. Rule 2, light will bend toward the normal when its speed decreases in a material. So here we have the incident ray, it's a medium 1. If the speed here is faster than the speed here, when it goes in, it's going to bend. So the incident angle here will be bigger than the refraction angle. In rule 3, light will bend away from the normal when the speed increases in a material. So coming out of this material here. It's slow, and then it goes into medium 2, which is fast, and so this is the normal. It's going to bend away. So the angle of incidence in this case is smaller than the angle of refraction. Video.
Now remember, refraction is the bending of light waves, or any kind of waves, as they change speed. And what we find is that as long as they travel through the same medium, they're traveling at the same speed, they travel in straight lines. But if I was to pour that water into this bowl, what would happen is the light would speed up upon leaving the water, and it would therefore refract or bend away from the normal. So what I can do is this: I can move back so I still see the dime, and as I lower this camera down, what happens is the dime becomes lost below the lip of that dish. Now that doesn't mean it's not still there. It just means that the light from it is above the camera right now, and therefore I can't see it. But what I'm going to do is I'm going to bend or refract the light of that coin back into the camera by pouring in this water. Now remember, light travels slower in water than it does in air. So when light leaves this water, it will speed up, and when light speeds up, it bends away from the normal. So in just a moment, you should start to see that coin as its light got bent away from the normal, which was above the camera, into the view of the camera. Now I'm simply going to pour the water back out of there, and it should disappear again. Now, because it's not being refracted, we can't see it unless we lift ourselves back up to where those light rays actually are.
So there's a good example of refraction and a cool magic trick. There's also partial reflection and refraction sometimes happening at the same time. And if you have reflection happening at the same time as reflection, we call it partial reflection and refraction. So light striking a water or a window, sometimes you can see the reflection on the surface, and sometimes you can also see something down below. Two-way mirrors and mirrored sunglasses also reflect a lot of the incident light. This is a good example of both of it because we have the mountain here, but it's also showing up in the water down below. In addition to the incident ray and the reflected ray, there's now this third ray, and we call it the refracted ray. The refracted ray is the one that bends when it enters into a second medium. So if it's leaving air and going into glass, that ray is not a reflected ray. It's not coming back out at us. It's going through the medium, so it is a refracted ray. And the angle of refraction is the angle between the normal and the refracted ray. When we draw the angle of reflection, we put a little r. The symbol for the angle of refraction is a capital R. Here's some nice other optical illusions based on refraction. And the next one, more of the same.
Can you see the gut? Is it hiding the gut? So I have breasts.
So those are pretty interesting because the light rays are not just being refracted once, they're being refracted multiple times. They're going from air through a medium of glass, through a medium of water, through the medium of glass, and then again through the medium of air. And because of that, there's multiple shifts in the refracted ray, and that changes the impression of what we see. Okay, so when we're basically drawing these ray diagrams, the top half here, oops, I should pick my pen tool. So this part here is what we did before with straight mirrors and curved mirrors. You had your incident ray coming in, and then your angle of incidence and your angle of reflection were the same with your reflected ray going out. Well, now when that incident ray goes into a medium, it's either going to bend towards this normal or away from the normal. And so what we need to know is what is the index of refraction between this one and this one? Or what is the speed in this one compared to this one? If the speed is faster here than here, it's going to bend towards the normal. And the only change is now this is the angle of refraction. So reflection is when it's coming off of the mirror or off the surface and coming back in the same side. And over here, refraction is when it's going through a mirror, a medium. Dispersion is a good example of refraction. When we take our glass prism, when white light goes in through a prism, it breaks up into the colors of the rainbow. And the reason why is because each of these has a certain frequency. They have a certain energy. We talked about that at the very beginning when we talked about the electromagnetic spectrum. We also talked that they all have different wavelengths. So when the white light comes in, and they all hit this new medium, they slow down. But when they slow down, they all slow down at different speeds because they already have different energies. And then that splits them up into their individual colors. Now, blue light is at the bottom, which means it bends more than red. And so blue travels slower than red.
When a beam of light hits a piece of glass straight on, it passes right through it. But the waves that make up the light actually get slowed down by the glass and only go back to their normal speed when they come out the other side. That slowing down is what causes white light to split into a rainbow of colour whenever it hits glass on an angle. It happens because glass slows some colours of light more than others, and because slowing down on an angle makes light bend. It's easy to understand the bending if you picture how the light waves would look from above, like how waves at the beach look if you see them from the air. And while white light's made up of all the different colours of light, it also helps to look at them one colour at a time. When a wave front of red light hits glass on an angle, the part of the wave that enters the glass first gets slowed down before the rest, and that changes the angle of the whole wave, like how waves bend around a cliff. Violet light gets slowed down even more by glass, so its waves bend more. All the other colours get bent somewhere in between. So the colours get separated when they first enter the glass on an angle, and they spread out even more when they speed up on an angle as they leave. The reason the different colours slow down different amounts in glass is because they've got different wavelengths. Red light has the longest wavelength, followed by orange, yellow, green, blue, indigo, and finally violet with the shortest wavelength. And the shorter the wavelength, the longer it takes to travel through glass. That's because light interacts with electrons in the molecules that make up glass. Long wavelength light, like red, only interacts a bit with the electrons, so it doesn't get slowed much. But shorter wavelength violet light interacts more, so it gets slowed down more. So it's the combination of hitting glass on an angle and different wavelengths interacting with the electrons in the glass different amounts that makes light hitting a prism spread out into a beautiful spectrum of colour. and some classic album cover art.
Okay, so that is dispersion. The idea that when light is reflected on an angle, it splits the beam up into the visible light spectrum. So again, here we have a guy who's going to harpoon our poor little Nemo fish, and this is actually Nemo. And when the light is leaving Nemo, it is going slower in the water. And then when it comes out into the air, it speeds up, so it bends away from the normal. But this guy, he thinks light travels in a straight line. So he sees Nemo over here. So if he started to harpoon over here, he'd miss Nemo and Nemo would get away and he's all okay. So the index of refraction is the amount by which a transparent medium decreases the speed of light. The larger the number, the more the medium decreases the speed of light. So a big number means slow, a low number means fast. So in a vacuum, it's 1, that's usually the fastest. And then, but if it was 0.8, then that would be even faster than in a vacuum. The speed of light would be going faster, or sorry, the speed of light coming through that medium would be faster than, say, 1.8. If it's 1.8, that's bigger than 1, so it's going slower. It slows down the light in that medium. So there's a nice calculation. This is called the refractive index of a medium. Is basically what we do is we take the speed of light in a vacuum and we divide it by the speed of light in the medium. And n is the index of refraction for that medium. So n is the index of refraction, c is the speed of light in a vacuum, and that is a constant. It is always 3.00 times 10 to the 8 meters per second. And v is the speed of light in a given medium. So because we're dividing speed by speed, meters per second by meters per second, we get rid of all the units, and so the index of refraction has no unit. So this is a good example. The speed of light in glass is 1.52 times 10 to the 8 meters per second. What is the index of refraction for glass? So we first think of our given, and we know that C is 3.00 times 10 to the 8. We know that V, our speed in the medium, is 1.52 times 10 to the 8. And now we want to get what is the index of refraction. So then we write our formula, n equals C over V, which is equal to 3.0 times 10 to the 8 over 1.52 times 10 to the 8. And we get an answer of 1.97. So therefore, the index of refraction for glass is 1.97. Here, the speed of light in water is 2.25 times 10 to the 8 meters per second. I'll just change the color here, blue. So here, if we look at our given, we have, again, C is a constant, it doesn't change. Our speed in water is 2.25 times 10 to the 8 meters per second. And now we have to figure out what is our index of refraction. So we write our formula, n equals C over V. We then put our numbers in for the letters. And when we do that, we get 1.33. So therefore, water's index of refraction is 1.33. The next one is just a little bit difficult because it's not as simple. We now want to get the speed of light in diamond. So here again, we have C is 3.00 times 10 to the 8 meters per second. Again, the speed of light in a vacuum is always the same. It is a constant. The V we don't know this time, but we do have N. N is equal to 2.42. So if I write my formula, N equals C over V, I want to get V. So if we look at how to isolate, I want to get rid of V, so I multiply on both sides to get V, because I don't want it on the bottom. So now I have V over N equals C. Well, to get V by itself, I have to divide by N. So here, V is equal to C divided by N. So now I can put my numbers in. 3.0 times 10 to the 8 divided by 2.42. And I get 1.25 times 10 to the 8 meters per second. So therefore, the speed of light in a diamond is 1.25 times 10 to the 8 meters per second. I just want to quickly show you how to do a ray diagram. If I had air here, and then I had a diamond here, so air's N is equal to 1.00, and in diamond, it's at 2.42. Is everybody okay with that? And I'm going to draw, this is my normal. Remember, these are supposed to be straight lines. You have to forgive me as I'm scrolling on my laptop as I'm trying to do this. So now, if I have my index of refraction, or my incident ray, sorry, this is my incident ray. It's coming in. Well, this here is a smaller number than this one. So this means this one is fast, whereas this is really slow. So what will happen is that when the light comes in, this is the incident angle there, angle of incidence. And then what happens is when it comes in, it's slowing down, so it's going to bend toward the normal. Okay, so what will happen is it's going to bend down, and this is the refracted ray, and this is our angle of refraction, R. So here, I is bigger than R. If I do another one here, say I was going from water, sorry, I want to do, again, I have my, so our normal. Here we have water and air. So water I think is about 1.5 and air is 1.0. So here it's going from slow to fast. Everybody okay with that? So if I had my incident ray coming in to the normal, this is again my incident ray, and this is my angle of incidence. What will happen is that as it goes out, it's going from slow to fast. That means it's going to bend away from normal. So here, I'm going to bend it away from the normal. And this is my refracted angle of refraction. And this is the refracted ray. And in this case, I is less than R. So that's how we're going to draw. We're not going to be necessarily in for this year, we're not going to be really picky. There is a way that we can calculate exactly what these angles are in each medium, but for this year we're not going to do it. So for this year you just have to know that if it's going from fast to slow, it's going to bend toward the normal, so it's bending this way. Whereas if it's going from slow to fast, it's going to bend away from the normal. All right, so let's explain the following. Why do we see the reflection of the sun at sunset, but never any other time during the day? So normally the sun's there, but there's no reflection. But all of a sudden at sunset, we see that beautiful glowing orb and the nice trails on the water. Well, the reason is because of the angle of incidence. So the amount of reflection compared to the amount of refraction depends on the angle of incidence as well as the relative indexes of refraction of the two substances. So if the angle of incidence is nearly zero, most of the light penetrates the surface and very little is reflected. As the angle of incidence increases, more light is reflected at the surface and less light penetrates the surface and is refracted. So in other words, when the sun is high in the sky, the angle is closer to zero, so more is refracted than reflected. Whereas as the sun is going down towards the horizon, there's a really big angle of incidence, so more light gets reflected, and we see that on the surface, and less is going through and being refracted. All right, so what did we learn today? So far, we learned that light goes from one medium to the other, and we have a little bit of reflection and refraction. So reflection would be over here. This would be reflection if it was coming this way, and this here, when it goes through a medium, is refraction. And we learned that light, when it travels from one medium to the other, either slows down or speeds up, and it'll bend toward the normal if the light is traveling slower in the medium, and it bends away from the normal if the light is traveling faster. So light will bend away from the normal when it speeds up at the boundary of two media. As the angle of incidence increases, the angle of refraction will also increase. So it's kind of like the angle of incidence equals the angle of reflection. But as we increase it, the bend becomes more and more pronounced. So here we have water going into air. So we're going from this one is slower, the speed of light is slower, and here it's going to be faster. So what will happen is because it's going from slow to fast, it's going to bend away from the normal. And here the angle of incidence is less than the angle of refraction. So this one here is smaller than this angle here. Now, what happens is as we continue to increase the angle here, if we make this angle continually get bigger, 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 this one's going to bend more and more and more and more until it reaches 90 degrees. So here we increase the angle, more bend. Increase the angle, more bend. Oh, this is 90 degrees. And what we start to see is there will be no more refraction. It'll get trapped. So the angle of incidence that produces a refracted angle of 90 degrees is what we call the critical angle. So in this example, we're saying 48.8 degrees is the critical angle. If light comes in on an angle of 48.8 degrees, it will refract straight along the surface. So this would have been a nice activity we would have done at school if we were there. So this is a media, it's a little glass semicircle. And here we have measurements of angles. And as the light is being shone through the media, the angle of incidence, there's very little refraction. It's going straight through. But as we increase the incident ray, there it's bending away, bending away, bending away, bending away, bending away, bending away. So as we keep increasing, the angle of incidence is getting bigger. The angle of refraction is getting bigger, but soon it's going to reach 90 degrees. And you can see what happens as it's nearing 90. As it gets to this 90, there is no more refraction. The light becomes reflected inside the media. Okay? So as we keep increasing, 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 the light is only being reflected inside the media. Until we're outside. Okay. So when it hits the critical angle, light, the refracted angle is 90 degrees and refraction doesn't happen anymore. No light ray comes through. It gets trapped inside whatever you're reflecting the light through, whatever the medium is. Okay, so if it's larger than the critical angle, all the light gets reflected back into the surface. This is what we call total internal reflection. So the critical angle occurs when the angle of refraction equals 90 degrees. If you increase the angle of incidence past the critical angle, the refracted ray no longer exits, and this is our total internal reflection. So here, as it's reflected down, nothing escapes, and it looks like the mountain is on the surface of the water. So for this to occur, though, the light has to be traveling slower in the first medium than in the second, and the angle of incidence is large enough that no refraction occurs in the second medium. Instead, it gets reflected back into the first medium. So if we look here, this is an incident ray. They're all incident rays here. And here I is just a normal eye, it's not critical, and we have the refracted ray here. Here in the red, this is the critical angle. So this refracts, the refracted ray is at 90 degrees. And in this case, it's the R is greater, that's the angle of reflection, is greater than the critical angle. Sorry, my dog is barking. R is greater than the critical angle, and so we get total internal reflection. The light does not escape out into the air. It gets trapped inside the media. So if light is traveling from water to air, it speeds up. The critical angle of water is 48.8 degrees. An angle of incidence greater than 48.8 degrees leads to total internal reflection. So if the angle is 55, the light doesn't get out, it stays in the water. If the angle was 46 degrees, we'd get refraction and reflection, a little bit of both. If the angle is 55, total internal reflection. If I is 24 degrees, we'd get just refraction. So why do we care about this? Because it gives a lot of cool uses that we see and use all the time.
Total internal reflection is important in technology. A lot of communications are done, including telephone and other communications. You may have an optical cable in your home stereo or home theater system that communicates audio information through an optical cable. The principle is total internal reflection. If we come in at a glancing angle, then all of the light that's incident on this surface and on this surface will be reflected back internally into the material. So it works for glancing angles, and the beam needs to be confined within a material that is more optically dense, has a higher index of refraction than the surrounding material. But any shape will do. You can use a rectangular shape here, you can use a circular shape, confining all that light inside of that fiber. This is a more typical light optical cable or light fiber. I'm just going to introduce the beam here. You'll see it come out on the far end. This is an example of, we have a source of light in the base here, and each of these, all they are strands of plastic, and they are channeling the light through them. And they can be bent or whatever, and they'll still channel that light. There is a certain radius. If you bend it, if you kink it really hard, then that brings you away from the total internal reflection, and you lose the effect. But very effective, very important in today's technology, total internal reflection.
A lot of the 5 and HDMI cables, all that sort of thing, rely on total internal reflection. Diamonds are a girl's best friend. So what happens is with a diamond, the light is coming in, and when it comes in, it gets refracted, and it gets split up, and it keeps bouncing around. So it hits at a critical angle, and then it can't escape. So if it's well cut, when it comes in, it's just going to keep bouncing around, and the only way it can go out is through the top. If the cut isn't proper, you'll get some refraction, but it won't be total internal reflection, and then you don't get as much of a shine and a sparkle. Same thing if the diamond is too shallow. Excuse me. You won't get the total internal reflection. You'll still get shiny and glittery, but just not as wow. So diamonds have a high refractive index, but a very small critical angle. So as long as the light comes in at anything greater than 24.4 degrees, you're going to get total internal reflection, which means the light can't escape except out the top surface, and it just gets bounced around several times before going out, and we get that nice, brilliant sparkle, sparkle, sparkle. Fiber optics, as we showed in the video, that's another good use for total internal reflection. It just basically passes the light along a glass cable, and the cable basically has a very small critical angle too, so as soon as light enters, it doesn't leave until the very end when it's allowed to escape out the end. It has a glass core that's surrounded by a cladding. This is the cladding. And the fiber core and the cladding are different types of glass. And then the cladding has to have a lower refractive index so that total internal reflection can happen. The coating and the strength member and the outer jacket, because these are glass, are easily broken. So you want to have a lot of protective layers just to protect the material that's transmitting the information. And again, telecommunication, television now, there's fiber optic cables that go all the way across the ocean. They can transmit multiple things. A lot of medicine endoscopes use fiber optics to be able to send light down into a very small place using a very small thing and be able to get images back too. So again, the light goes in, gets bounced, total internal reflection until it comes out the end. Prisms are another good use of total internal reflection. So by having the light come in, it gets reflected only in one way and comes down, and we're able to see the image there. There's basically two ways we can do it. We can do it like a right angle where the light's coming in this way, hits at 45 and reflects down at 45, or we can do a double, which is a 180. So if we turn it sideways, the light comes in, hits this side, goes down and hits this side, and then reflects back out. So these are using periscopes. Here is where your eye is. The light's coming in, hits a prism, bounces down, and then hits another prism and bounces back out. In binoculars, we have things coming in through a lens. They hit some prisms here and bounce back up to the ocular where we see the image. Cameras also, you make use of multiple prisms to be able to reflect the light back to our eye. Retroreflectors are when rays get reflected back in the exact same direction as the original incident ray. And in other words, they don't get reflected on the other side of the normal, they get reflected on the same side of the normal. And this gives us two total internal reflections. So things like our road signs, reflective strips, those little lights you put on your bikes that reflect the light back, all of those things are called retroreflectors. The LR3 is an array of retroreflectors placed on the moon, and because of the information that it is gathering, they've been able to determine the distance to the moon using it. Now, what are some of the phenomena related to refraction? First is apparent depth. So here we again have the chest. The light is going from a slow medium into a faster medium, so it bends away from the normal, but the human thinks our eyes know that light travels in a straight line, so we extend the reflected ray straight, and we see the image kind of floating in the middle here, and that's what we call apparent depth. And that's basically an optical illusion. So it's also like that one that we showed earlier with the dime where we can't see it, but when we add water, it bends the light, and now it looks like the dime is near the top of the water. That's apparent depth. The mirage. So the idea of people crawling through the desert and thinking they saw the oasis, or when you're driving along the road, you see shimmering, it looks like the road is wet. Well, when the sun shines on pavement, it absorbs a lot of heat, and the hot pavement warms the air. So light traveling from cool air into warmer air. And since the index of refraction is different in cold air than warm air, and it decreases as the air gets warmer, this results in light bending farther away from the normal as the air heats up. So as it bends so far away from the normal, that total internal reflection occurs in the hottest air mass. And the reflected ray then refracts upwards toward your eyes, which goes from hot air to cooler air, and our eyes trace it back in a straight line to the ground. So we see this image to be water, but really it's just a virtual image of the sky. So here in the oasis, there's a tree. The sunlight reflects off the tree, and we kind of see that. But some of the reflected light goes down towards the observer where it is then refracted. And then we see an upside down image, and it looks like the mirage, like the oasis is on the sand. Shimmering, that idea of the moon seems to have cast a nice shadow over the water. Moonlight passes through layers of air that have different temperatures. In coldest air, light travels slowly, so the light rays will bend towards the normal. But as it gets closer to the surface of the water, the air is warmer, so its speed increases, causing the light rays to bend away from the normal. And this starts total internal reflection in the lowest warm air layer, and we see multiple virtual images of the moon on the surface. So all this white stuff is basically a whole bunch of little virtual images of the moon being cast down because of the difference in air temperature. The rainbow is an example of dispersion, which we talked about earlier, where it basically separates the light from white light into the visible spectrum. And it's basically an optical phenomena produced by water droplets in the atmosphere. So the light is refracted as it enters the raindrop, resulting in dispersion. Then the light hits the back of the raindrop, resulting in partial internal reflection. Then it's refracted again as it leaves the raindrop. And then this light hits your eyes and your brain forms a virtual image. This kind of shows why it seems to be upside down.
Surely you've seen a rainbow. Maybe you were chasing tornadoes and happened upon one. But did you ever notice that the sky is darker above a rainbow than below? I never did until someone pointed it out. We're gonna find out why this is so with the help of refraction of light, dispersion, and the incomplete story you're usually told about why rainbows form. This story starts with refraction, the bending of light as it moves from one medium, like air, to another medium, like water, at an angle. Light actually slows down in water. Visible light would take 11 minutes instead of the usual 8 to get from the sun to the earth if there were a giant ocean in between. So as light slows down when it enters water, the beam is forced to turn. But unlike the constant speed of light in a vacuum, the speed of light in water depends on the color. Violet light moves slower in water than red light, so it will bend more as it enters the water. An incoming beam of white light will be spread out and separated into a spectrum of color. We call this dispersion. Now let's take this white light beam and send it through a droplet of water. Some of the light will refract into the droplet, then reflect off the back and refract back out to travel down to your eye, typically at an angle of 42 degrees between the incoming light and the outgoing light. This can occur in a circle of droplets, so if the ground weren't in the way, rainbows would be a full circle. Here's the fun part. Violet light refracts more in the water droplet than red light, as we discussed, so violet light should end up exiting higher in the water droplet than red. But if we look in the sky, red light is clearly higher than violet light. What's going on? Well, if you're observing from down here, this water droplet will only send red light to your eyes, and the violet light will pass above you. It's the droplets down here that send violet light to you, and the violet light will appear to be coming from lower in the sky, as it does. And that's how we get our colors in the rainbow from rain and sun. End of story. But there's one part I never understood. Why should all of the light enter the water droplet right at this point? Well, the answer is it doesn't. Some red rays enter here, some enter here, and they all exit in different directions. If we add back in the other colors, you end up with an exiting, jumbled mess of color. This mess of color should look white, but it definitely doesn't. So what's going on? This is where it gets more complicated than you usually hear. As this red light ray enters higher from the midpoint, it exits at an increasingly large angle. But watch what happens here. Eventually the ray turns around. No matter where red light enters the droplet, it can't go past this angle. That's the maximum angle, and it's 42 degrees for red light. It's slightly less for orange and yellow and so on until you reach violet, where the max angle is 40 degrees. So it turns out that at that maximum angle, you also get a maximum brightness. So even though all the colors can reach here around violet's max angle, because their maximum is beyond that, violet is at its maximum brightness, so it stands out against the other colors. Same goes for the max of the other colors. Below violet, no colors are at a maximum, so all the colors mix again and form white. That's why the sky appears lighter below the rainbow than above. None of the light can make it out above red, so the sky appears darker. Then how did this second rainbow sneak up there? Well, you'll notice the colors are flipped in order, and again that the sky is lighter above them. That indicates that the light had to reflect twice inside the droplet. In order to get the right angle down to your eye, it actually had to enter the droplet from below the midpoint, and you get a double reflection, causing a second rainbow. Now the story is complete. The end.
So more information about a rainbow than you probably thought you needed. But basically the idea is that sunlight comes in, it gets refracted, and the red is up high, so it looks at the top, whereas when it's coming through, we see the purple down lower so that when it hits our eyes. So, and then all the other colors are obviously in between to form the rainbow. And now we are done. Sorry this one took so long, folks. I promise it is a lot easier work though, if you watched it all, because there's just a few little calculations and it won't be as much drawing as you normally have to do. So have a good week. I'll talk to you this week at our session. Hopefully I'll see you there, but enjoy yourselves. Bye.